Hello guys, welcome to our fourth video. This is TutorMed, where everything medicine is simplified. And the name has not changed. My name is Kofi. I am a medical officer with the Department of Internal Medicine and Therapeutics at the Holy Family Hospital, Techiman. And guys, thank you for the support you've given this channel and for keeping me on my toes to bring the very best. I really appreciate that with a thumbs up. I really appreciate that. We dealt with one lab investigation in our last video, and if this is news to you, kindly find in the description below the link to the interpretation of the hepatitis B profile. Today, we want to look at another important investigation in our practice, which in my opinion should be the first investigation every doctor or medical student should master its interpretation: the full blood count. Kindly continue supporting us by subscribing to our channel, sharing and liking our videos, and leaving your comments in the comment box. We really appreciate that. Alright guys, let's get started. The full blood count is also known as a complete blood count. And as usual, before the interpretation, we need to establish principles. Blood has a liquid component called plasma, which predominantly is made of water, and a solid component made of blood cells. And with the FBC, or the full blood count, it is the blood cells you are interested in, although conditions which affect plasma volume, such as dehydration, fluid overload, can also affect the count of these cells, giving a false cell count. If this does not make sense now, do not worry. We will illustrate this later. However, let's begin with what these blood cells are, their functions, and where they come from. In the adult, the cells of the blood are produced by the red marrow of the bones of the axial skeleton, like the vertebrae and the skull, and also produced from the proximal ends of the long bones, like the humerus and the femur. There are three groups of cells in the blood. The first is the red blood cells, also known as erythrocytes. Their function is to carry oxygen to tissues for use, and then carry carbon dioxide to the lungs for excretion. The second group is called the white blood cells, also known as leukocytes. Their function is to fight infections and get rid of foreign tissues or foreign antigens. The last group is the platelets, also known as thrombocytes. They help in blood clotting. Mature red blood cells contain hemoglobin, an iron-containing molecule which turns red when oxygen is bound to it. And it is oxidized hemoglobin which is responsible for the color of these red blood cells. Platelets are actually not cells, but cell fragments. Among the red blood cells, they may differ in sizes, but they have similar structure and function. The same goes for the platelets. However, for leukocytes, which are white blood cells, there are different kinds, and they perform different functions. Generally, they come from two ancestries or origins. We have the myeloid and the lymphoid. So for those who come from the myeloid ancestry, the first one, we have the granulocytes, which are white blood cells which contains granules. There are three kinds: the neutrophils, the eosinophils, and the basophils. The granulocytes can be remembered by the acronym BEN, B for basophils, E for eosinophils, and N for neutrophils. The next group of the myeloid descendants are the monocytes. Now let's take a look at those which come from the lymphoid ancestry. Together, these are called lymphocytes. We have the B lymphocytes, the T lymphocytes, and the natural killer cells. You may be wondering, where are the macrophages and where are the mast cells? Well, when monocytes leave the blood and enter into tissues, they become macrophages. In other words, a macrophage is an extravasated monocyte. And we can say same for the mast cell. When a basophil leaves the blood and enters into tissues, it becomes a mast cell. A mast cell is an extravasated basophil. And so the white blood cells featured on a full blood count report with differentials are the neutrophils, the eosinophils, the basophils. These three form the granulocytes, the monocytes, and then instead of showing the individual lymphocyte types like the B cell, the T cell, or the natural killer cell, they are all grouped as lymphocytes on the report. And so, observing precautions, we sample about 3 ml of venous blood and put this sample in an anticoagulant coated bottle. The most common one here is the EDTA bottle, ethylene diamine tetraacetic acid bottle, and then swirl the bottle up and down gently to prevent lysing the red blood cells, which can affect our report. This sample is then analyzed by the automated cell counter or the hematology analyzer. The analyzer just takes a small quantity from the specimen bottle and analyzes it. Then, after analyzing it, it shows the profile of the patient's blood cells, the patient's RBCs, WBCs, and then platelets. And so what does the analyzer tell us about the red blood cells? Remember we said the analyzer takes a small volume of the sample we took and analyze it? The analysis of that representative sample gives a reflection of the patient's entire blood. So the first thing the analyzer tells us about the red blood cell is the red blood cell count. It tells us how many red blood cells there are in that volume. It does so by counting the number of cells and expresses it as 10 to the power 12 red blood cells per liter. So for example, we can have a patient's red blood cell count as 3.0 times 10 to the power 12 cells per liter. Also recollect that we said hemoglobin occupies the space in red blood cells. So after counting the number of cells, the next thing it does is to add the masses of the hemoglobin molecules in all the red blood cells it counted and then document it as the hemoglobin content. And so the hemoglobin content tells us the total mass of hemoglobin molecules in the blood. It is expressed as gram per deciliter. For an example, we can have a patient's hemoglobin content as 12.3 grams per deciliter. After telling us the total number of red blood cells and the total hemoglobin content of our sample, the next thing it does is to tell us the hematocrit or the packed cell volume. Remember we established in the beginning that blood has a liquid component called plasma, which is represented by this straw color in this specimen, and then a solid part which is made up of cells. The solid part is composed of this buffy coat formed by the platelets and the white blood cells, and then this packed cell volume which represents the entire red cell mass. And so the hematocrit answers the question that the total number of red blood cells counted initially, what percentage of blood volume does it occupy? And the result is expressed as a percentage. So for example, a patient can have a hematocrit or packed cell volume of 42%. This means the red blood cells occupy 42% of the entire blood volume. Next, the analyzer tells us about the red cell indices, the first being the mean cell volume. The red blood cells in our sample have varying sizes. Some are big, some are small, and some have intermediate sizes. And so the mean cell volume answers the question, what is the average size of the red blood cells counted? It is expressed in liters as femtoliters. So for example, you can have a patient whose mean cell volume is 80 femtoliters. The next RBC index is the mean cell hemoglobin. Actually, what accounts for the different sizes among red blood cells is the varying amount of hemoglobin in them. The mature red blood cell has no nucleus, and since hemoglobin is the predominant molecule inside, its content or amount will determine the size of the cell. This means the plentier your hemoglobin, the larger your size. And so varying cell sizes indicates that the red blood cells have different hemoglobin content. The mean cell hemoglobin answers the question, what is the average mass of all the hemoglobin molecules of the red blood cells we counted in that sample? And the answer is expressed in grams as picograms. So for example, a patient can have a mean cell hemoglobin of 26 picograms. The next is the mean cell hemoglobin concentration, MCHC. Hemoglobin occupies a certain volume within the red blood cell, and this represents its concentration within the cell. So, we are asking the question, what is the average concentration of hemoglobin in the red blood cells we've counted? This is expressed as gram per deciliter. The last red cell index is the RDW, the red cell distribution width. Since there are varying sizes, some are small, some are big, some have intermediate sizes, we want to know how varied the sizes are. Alright guys, now let's move to the white cell parameters. So the first thing it shows is the total white cell count, after which it gives the white cell differentials. So for the neutrophils, it shows its absolute count and its relative percentage. That is, the absolute count of neutrophils over the total white cell count times 100. Next is the lymphocytes. It shows its absolute count and its relative percentage. Then we have the basophils, its absolute count and its relative percentage. Followed by the eosinophils, again its absolute count and its relative percentage. Then lastly, the monocytes, its absolute count and its relative percentage. And so from there, we move to the last cell type, the platelets. And here, the analyzer shows us the platelet count and the platelet indices, just like it did for the RBCs. And so the total platelet count tells us the total number of platelets per unit volume. And then we move to the mean platelet volume, which is the equivalent of the mean cell volume for RBCs. Just like the RBCs, there are different platelet sizes, but the MPV or the mean platelet volume tells us the average size of the platelet. Then we move to the platelet distribution width, which is just like the RDW. And then lastly, the platelet crit, which is like the hematocrit. Alright guys, please don't forget to take a break to like and share our video and subscribe to our channel. Now for the RBC parameters, what are the steps to interpret them? First, we want to know if our patient is anemic. And anemia is defined as the reduction of hemoglobin content depending on the age, sex, geography, and physiological status of the patient. It is dependent on age because, for example, children generally are expected to have a higher HB than adults, And so an HB might be considered normal for adults, but for children it may be low. And for the sex of the patient, men are expected to have a higher HB than women. 1, because of menstruation in women, and 2, because men have testosterone in them compared to women. And so testosterone is known to stimulate erythropoietin, which also increases the production of RBCs. So an HB in women might be considered normal, but the same HB might not be considered normal for men. Then for the location, people at higher altitudes are expected to have a higher HB than those at the low altitude. And so an HB might be low for a person at the higher altitude, but might be normal for a person settling at the low altitude. Then lastly, the physiological status of the patient. Pregnant females are expected to have a relatively low HB compared to non-pregnant females. And so in defining anemia, all these parameters have to be put or taken into consideration. Now, to identify a patient with anemia on the full blood count, the RBC count, HB, and hematocrit can all be used, but we look at the HB content to identify anemia. So what we do is we compare the patient's HB to the range we have. So for men, the range is 13.5 to 18 grams per deciliter, and in women, 11.5 to 16 grams per deciliter. Now, after we have identified that the HB is low, the next thing is to identify its probable cause, still on the FBC report. And we do that by looking at the MCV and the MCHC. The mean cell volume has a normal range of 80 to 100 femtoliters. And then the mean cell hemoglobin has a normal range of 27 to 32 picograms per cell. We will see how to use this to identify the probable cause later. Now, I must point out the fact that before you use the MCV and the MCH to guide you to identify the cause of the patient's anemia, you should have taken a history and a physical exam. Now, the next is to determine the severity of the low HB. And the low HB is said to be mild if it is from 10 to the lower limit of the normal range. It is moderate if it is from 8 to anything less than 10, so it could be 9.9. And it's said to be severe if it's from 6.5 to anything less than 8, like 7.9. And said to be life-threatening if it's less than 6.5 grams per deciliter. Alright guys, now let us review how the causes of anemia can be classified. So we can classify anemia as anemia due to ineffective production, anemia due to increased distraction or sequestration, and anemia due to blood loss. And so for anemia due to ineffective production, the patient is anemic because you are not producing the red cells enough. So here, it could be due to deficiency in the raw materials used in the production, like iron deficiency. Or it could be due to the fact that the site of production has a problem, and so bone marrow failure. It could also be due to the fact that the bone marrow is working, there are raw materials, but there are inhibitors of production in the system, like lead poisoning. The second classification is anemia due to increased distraction or sequestration. So here, we are producing enough red blood cells, but at the same time, we are destroying them. So causes include hemolytic anemias like G6PD deficiency, severe malaria, or sometimes we may not be destroying them. But then, the spleen normally sequesters about 5% of blood cells, but when it becomes hyperreactive, it can sequester so about 40%, causing reduced red blood mass or red blood cell mass. And so hypersplenism can also cause anemia. The last classification is anemia due to blood loss. and the blood loss could be a chronic blood loss, which might result in iron deficiency anemia, or it could be an acute blood loss. So looking at these wide range of differentials, how can one narrow his differentials using the full blood count report? To do that, we pay attention to the MCV and the MCH. So looking at the MCV, which has a normal range of 80 to 100 femtoliters, we say the cells are microcytic when the MCV is less than 80, normocytic when it is between 80 to 100, and macrocytic when it's above 100. And then using the MCH, which has a range of 27 to 36 picograms, we describe the cells as hypochromic when the MCH is less than 27, normochromic when it is between 27 and 36, hyperchromic when it is above 36. Please remember that the HB content of a cell corresponds to its size. So if a cell is microcytic, which means a small sized cell, it is likely that it has little HB inside. And so we can have a microcytic hypochromic anemia. And what are the causes? What can cause cells to have a low HB or little HB inside them? It can be due to the fact that the raw materials needed to produce the HB is deficient, and so one of the components of the HB is iron. So if iron is deficient, it can result in microcytic hypochromic anemia. The other causes are thalassemia, sometimes anemia of chronic disease, sideroblastic anemia, and sometimes lead poisoning. So the causes of microcytic hypochromic anemia can be remembered by the mnemonic TAILS. T for thalassemia, A for anemia of chronic disease, I for iron deficiency anemia, L for lead poisoning, and S for sideroblastic anemia. Then the next is normocytic normochromic, normal size, normal HB. The causes are anemia of chronic disease, acute blood loss, and then most hemolytic anemias. Now when the MCV is greater than the upper limit of normal, then we have a macrocytic anemia. And here we expect that the HB will also be hyperchromic, but we usually do not add that. So macrocytic anemia can be divided into megaloblastic anemia and non-megaloblastic anemia. The causes of megaloblastic anemia include vitamin B12 deficiency, folic acid deficiency, use of chemotherapeutic drugs like methotrexate, and sometimes HIV and AIDS. These anemias are characterized by megaloblasts, which are found in the bone marrow. Then we have non-megaloblastic anemia. Causes include alcoholism, chronic liver disease, hypothyroidism, reticulocytosis, to mention a few. The last parameter is the RDW, which tells us the variation in the sizes of the red blood cells, or the degree of anisocytosis. Using the iron deficiency anemia and thalassemia as examples, both would have microcytic hypochromic anemia, but the RDW will differentiate between the two. It is normal in thalassemia but high in IDA. Sometimes, instead of anemia, our patients may have polycythemia, and here the HB is higher than the upper limit, and so for women we have HB more than 16.5, and for men more than 18.5. This is usually accompanied by an elevated hematocrit, which for men is more than 50% and for women more than 44%. For polycythemia, we have two types, the absolute polycythemia and the relative polycythemia. We will look at them in a minute. Please remember that in the beginning of the lecture, we said plasma volume changes can affect the parameters of the FBC. Please remember that. Now for absolute polycythemia, the hematocrit proportion, which is the actual red blood cell mass, is actually high and the plasma volume is unchanged. The hematocrit has not increased because something affected the plasma volume. Comparing that to relative polycythemia, here something has happened to the plasma volume. It has reduced either through dehydration or another pathology, thereby falsely increasing the hematocrit, otherwise known as hemoconcentration. Now let's see how to illustrate this. There is a concept in hematology called the hematology rule of threes, which states that the RBC multiplied by 3 should give you the hemoglobin, and that answer multiplied by 3 should give you the hematocrit plus or minus 3. And this rule is valid if the RBC indices are normocytic, normochromic. So for an example, we have a patient whose RBC count is 4.1 times 10 to the power 12 cells. The rule says that if you multiply 3 by 4.1, you get an HB of 12.3 grams per DL. And if you should multiply the HB by 3, you get a hematocrit 36.9 plus or minus 3. And this is only valid if the RBC index is normocytic, normochromic. And so in relative polycythemia, the rule of threes is not obeyed. You would have a high HB, but when you multiply by 3, it won't match the hematocrit. However, it is worth pointing out that a hematocrit more than 60% is almost always indicative of absolute polycythemia. Absolute polycythemia can be grouped into primary and secondary absolute polycythemia. For the primary one, polycythemia rubra vera is the most frequent cause. Conditions which cause chronic hypoxic states are responsible for secondary polycythemia because the chronic hypoxia will stimulate erythropoietin release, which would cause increased red cell production. So conditions like COPD, smoking, and then cyanotic heart disease. Then for the relative polycythemia, we have dehydration. Secondary polycythemia or secondary absolute polycythemia is the most common cause of polycythemia. So now let's look at the RBC interpretation summary. First, look at the hemoglobin content and determine whether the patient is anemic, normal, or polycythemic. If the patient is anemic, determine its severity, whether it's mild, moderate, severe, or life-threatening. And then determine its likely cause using the MCV and the MCH. Examine the RDW if necessary. If the patient is polycythemic, please determine if it is absolute or relative polycythemia using the hematocrit level and the rule of threes. Now let's move to the WBC interpretation. Here, you first look at the total WBC count. Determine if it is elevated or reduced. The normal range is 3.6 to 11 times 10 to the power 9 cells per liter. And so you are said to have elevated WBC count or leukocytosis when the WBC is more than 11, and then leukopenia, which is reduced cell count, when the WBC count is less than 3.6. The causes of leukocytosis: it can be in response to an event, in which case it is described as reactive, so such as infections, inflammation, post-surgery, and then the use of steroids. Another cause is also hematological malignancies. And so what are the probable causes if there is leukopenia. It could be due to overwhelming infections, bone marrow failure, use of cytotoxic chemotherapeutic drugs, and then medications like some antibiotics. Now let's turn our attention to neutrophils. When the bone marrow produces neutrophils and they get into circulation, they are classically divided into two groups: those which are circulating and those which are attached to the endothelium. So we have the circulating pool and the marginal pool, about 50% of them each. The circulating pool contributes to the count we see on the full blood count. The normal range is 1.8 to 7.5 times 10 to the power 9 cells per liter. And neutrophils generally form about 40 to 70% of the white cell population in blood. And so when the neutrophil count is elevated, it is known as neutrophilia or neutrophilic leukocytosis. And some causes include acute bacterial infections, inflammation and tissue necrosis from myositis, vasculitis, or even necrosis from cardiac infarct. Asplenia can also cause neutrophilia because usually the spleen sequesters a proportion of white blood cell from the circulation, and so if there is asplenia, that proportion would get into circulation and increase the neutrophil count. Corticosteroid therapy can also increase the neutrophil count because it impairs the adherence of the marginal pool onto the endothelium, and so that pool also gets into circulation, contributing to a high neutrophil count. And then cancers in general. Neutropenia can be caused by a normal variant. Africans are allowed to have neutropenia to about 1.5. So that's a normal variant called benign ethnic neutropenia. It can also be caused by overwhelming infections. Hypersplenism, that is when the spleen sequesters more than it should, and then the use of certain chemotherapeutic drugs. If the absolute lymphocyte count exceeds its upper normal limit, we have lymphocytosis. Some causes include acute bacterial infections like pertussis, acute viral infections like infectious mononucleosis, infectious hepatitis. We have chronic infections like TB. We have MI, trauma, major surgery, cigarette smoking, malignancies like chronic lymphocytic leukemia and acute lymphocytic leukemia. Now let's look at some causes of high eosinophil count called eosinophilia. We have allergies, parasitic infections, drug hypersensitivity, some skin conditions, and then a type of vasculitis called Churg-Strauss syndrome. Causes of elevated monocytes or monocytosis, we have chronic bacterial infections like TB, typhoid. We have connective tissue diseases like SLE and rheumatoid arthritis. Now let's look at platelet interpretation. When platelet count is less than the lower limit of the range, then we have thrombocytopenia. Some common causes include 1. Clotted sample. When the sample collected is not mixed properly with the EDTA in the tube, the blood clots and gives a falsely low platelet count. But generally, thrombocytopenia can be grouped into two broad causes: decreased production by the bone marrow or increased destruction or use. Typically, thrombocytopenia with low mean platelet volume or MPV is associated with hyperproliferation of the bone marrow, and aplastic anemia is one of the common causes. And then thrombocytopenia associated with a high MPV is associated with increased destruction or use. And so we have immune thrombocytopenic purpura, inflammatory bowel disease, disseminated intravascular coagulation, just to mention a few. Now, in rare cases, the EDTA in the tube can cause an unusual platelet aggregation and result in thrombocytopenia. Also, overwhelming sepsis can result in thrombocytopenia, and this will fit into the category where the platelet count which is reduced is from increased distraction or use. For the causes of thrombocytosis, which is an elevated platelet count, just to mention a few, you have essential thrombocythemia, which is a myeloproliferative disorder where platelets are overproduced. Then we have iron deficiency anemia. It is actually an association and a reactive thrombocytosis. And then many inflammatory states can result in thrombocytosis because platelet is an inflammatory marker. Now, sometimes all three cell lines can be reduced, and this is called pancytopenia. There are many causes of pancytopenia, but the mnemonic I use to remember them is Her Royal Majesty Sarah Button sincerely danced alongside Prince Callister. Hair for hypersplenism. Royal for radiation, exposure to radiation. Majesty for megaloblastic anemia. Sarah for SLE or systemic lupus erythematosus. Button for bone marrow infiltration. Sincerely for subleukemic acute leukemia. Danced for drugs. Alongside for aplastic anemia. Prince for paroxysmal nocturnal hemoglobinuria, PNH. And then Callister for chemotherapy.